All right, so let's continue our discussion of the Diels-Alder cycloaddition. So again, what we have here is a diene combining with a dienophile. And so this is the dienophile, and this in this case is ethene. But this reaction is very slow. And that's because both the diene and the dienophile both have essentially the same electron density, whereas in most cycloaddition reactions, the diene is electron rich, while the dienophile is electron poor. And so we can make this reaction faster if we add EWGs to the dienophile. And so EWG stands for electron withdrawing groups. And so these are things that are going to make this dienophile more electron poor, which will allow the reaction to happen at a faster rate. And so something like this can be like an aldehyde, right? Think about the resonance structures. These pi electrons can go up into here, up into the oxygen, and so making the pi bond more electron poor. You can use all kinds of carbonyls. You can use esters or carboxylic acids. They'll both work. Another good one that's not a carbonyl is a cyanide group. That's also very, very commonly used, but it's mostly carbonyls. And so there's some cyclic carbonyls as well. The most popular one is maleic anhydride, which is this compound right here. And so you can see it's got two carbonyls in it, and so it's very electron withdrawn. Or we could have the cyclohexane dibenzoquinone as well. And so if you think about all of these alkenes, they're all poor or electron poor, which make them a good dienophile. Right, those are all electron poor. It doesn't have to be an alkene though. Alkynes will also work as the dienophile. So for example, you could have a diene, and then for your dienophile, we could have an alkyne. And so the mechanism here is the same. But if you think about the electrons and how many there are, we're still going to be left with a pi bond on our cyclohexane. So our product now will have two pi bonds, where this pi bond came from our alkyne.